So the electricity topic starts with some Nat5 stuff. So quantity of charge measured in coulombs is current measured in amps times time. The only other formula with quantity of charge in is this formula we looked at really when we looked at electric fields. So the voltage of an electric field is the energy in joules. Remember, work is an old-fashioned word for energy. So voltage is the energy given to each coulomb of charge Q. So with circuit analysis at higher, the most commonly used formula is still V equals IR. We are quite often wanting one of those three quantities to do with a particular component, and so we use circuit analysis, which we'll talk about, we'll remind ourselves about in a bit, in order to find two out of those three quantities, and then we can do V equals IR. We've got the power formulas along the bottom, which is still sometimes used in higher. P equals IV, P equals V squared over R, P equals I squared R, and P equals E over T. And then we have the finding the total resistance of components in a circuit, and this top one is to do with series, when components are in series, and this bottom one is to do with when components are in parallel. And at higher, it's pretty common to have like a cheeky combination, so you use the parallel one first and then the series one, or maybe the series one first and then the parallel. So just go with whatever is going to simplify the circuit sooner. So the definition of voltage: what is voltage, what is EMF? Voltage, EMF, is the energy an electric field gives to each coulomb of electric charge within that field. The object that carries that electric charge gets given energy, and we talked about this. W equals QV. The energy equals the charge being carried times the voltage of the electric field. So that's the energy which the object carrying the charge ends up being given. Q is the quantity of charge that object is carrying, and V is the voltage of the electric field. You get you typically work out the energy which the object carrying the electric charge gets given by the electric field, and then you can put that into this formula, EK equals half mv squared, because you worked out that the mass typically of a proton or an electron, well, that's on the data sheet, and you can solve to find the speed which it goes at as a result of being in the electric field. So we quite often think about voltage being like an electric pressure, even though it's actually a force field. So the voltage gives like an external electric field, and the charge carrying particles have their own little electric field. So maybe these are electrons, and you can see their own little electric field in red, which are responding to the overall external electric field, which I've shown in black. So just to kind of really go over the point, for example, a 1.5 volt battery means 1.5 joules of energy is being given by the electric field, by the external electric field, to each chunk or each coulomb of charge. So here's the circuit analysis, which we mentioned before. This is just the same. Well, to begin with, the left hand side, it's just the same as Nat5. So a series circuit is a circuit where there's just one loop. So in here we have a battery, a resistor, and a bulb. Now in a series circuit, the current is the same in all parts of the circuit. So in this case, I1 is the same as I2. The supply voltage, Vs, is shared out, it's totally shared out between the components in the circuit. So the supply voltage here is equal to V1 plus V2, and components which have a big resistance end up with a big share of the total voltage push. Now it kind of makes sense that voltage push is shared out, because in a series circuit there's just one pipe, it's just one loop, so of course the total push has to be shared out between components in that one pipe. There is only one pipe, and so everything in it has to share the pressure. If you want to work out what share of the total voltage push a particular component gets, you use these formulas. These are the voltage sharing out formulas. So parallel circuits are used much more in everyday life, because they are independent loops that just happen to connect, but still independently, with the same voltage supply. So for example, here's hair straighteners and a lamp. Each of these is an independent loop. So the blue loop is the hair straighteners, it's the heater, and the red loop is the bulb for the lamp. They are independent loops, they just happen to share the same voltage source. So it kind of makes sense then that if they have independent connections to the same voltage supply, that each of those independent loops have the same voltage push as is the voltage supply. So here, supply voltage Vs equals voltage across loop 1, which equals voltage across loop 2. Another way of thinking about this is all electrical appliances which you may buy for the home, they're all designed to work with 230 volts, which is mains voltage. So yeah, everything's plugged into the mains in parallel, everything gets 230 volts. The current going through the voltage source is the current through each of the loops added up, which kind of makes sense. An analogy we used at Nat 5 is the total customer current leaving Tesco is the current through each of the checkouts added together. With a battery, if you hook a battery up to an oscilloscope gives a picture of what a voltage is doing over time. It's like a graph of voltage against time, and so a battery, it has a nice steady push, and so it looks like that. If you flip the battery around the other way, it has a nice steady push, but it's negative, showing that the push is going in the opposite direction. That's called direct current. With the mains is alternating current because of the way it's made in a power station, and so it pushes forwards and then it pushes backwards and forwards and backwards and forwards, and I suppose the current never actually goes anywhere as such, it just goes forwards and backwards and forwards and backwards and forwards and backwards. So the red part here is the forwards push, and the back part is, and the black part is the backwards push. So if you've got a voltage time graph, you can find how long it takes to do one forwards and backwards push, or one forwards and backwards cycle, and this is known as the time period. It's the well, it's kind of like wavelength, except it's to do with time because the x-axis is time. So it's typically the distance between peaks, or you could do the distance between peaks, or the distance between troughs, or you could do the distance between middle bit and distance between middle bit. Anyway, the time period then allows you to find the frequency by using the formula frequency is 1 over t, which is the number of times the push goes forwards and backwards every single second. So with the mains, the time period comes out to be 0.02 seconds, and if you do f equals 1 over t, the frequency comes out therefore to be 50 hertz. So the mains pushes forwards and backwards 50 times every second. But not all alternating current supplies have the same time period and frequency as the mains. So for goodness sake, if you're given an alternating current thing to work out, don't just assume it's going to be exactly the same as the mains. So here's an oscilloscope trace of an alternating current source. We've talked about the time period. We sometimes have to read off the peak voltage. A part of this is using the scale. So an oscilloscope has like a grid background, a bit like graph paper, and the Y gain just tells you, it's sort of like a scale for the boxes vertically. So it tells you how many volts each box represents. And then you count up the number of boxes and say, I don't know, well, if that's 4 boxes going up and each box represents, I don't know, 0.5 volts, then 4 lots of 0.5 is 2 volts, and so the peak voltage is 2. The time base is exactly the same idea, but for the x-axis, so it tells you, yeah, it's a scale for the boxes horizontally, so it tells you how many seconds each box represents, and then you can count the number of boxes and multiply it up. Time is often given in milliseconds, so watch out for that. Now, look at the peak voltage of an alternating current supply. Peak voltage, yes, you get peak voltage, but you get it for such a tiny, short amount of time. That's not really representative. It's not really correct to design electrical appliances which need that level of peak voltage all the time in order to work, because you don't get that peak voltage all the time in order to work. So you don't get that peak voltage for all the time. You get it for kind of a very brief instant. So you can't design an appliance to work with peak voltage if that appliance needs the steady a steady voltage of that peak voltage, because it won't work. So what we do is we take a value which is about 70%-ish of that peak voltage, and we say that that is much more representative of what you're going to get. So appliances are designed to work if they need a constant voltage push, which is what the overwhelming majority of appliances do need. Then they're designed on the principle that what they're going to get is about 70% of the peak voltage. Now, don't go with 70%. How you actually work out what you get, what you effectively actually get, is called the RMS, and voltage RMS is the peak divided by root 2. And because voltage pushes current around the circuit, current RMS is the peak current divided by square root of 2. All right. Another definition is that the RMS value of voltage is the battery voltage you would use if you were going to replace the alternating current supply with a direct current supply. The battery voltage you would use to replace the alternating voltage supply with a direct current supply if you were going to do that. Batteries ain't so perfect. So here's an experiment. We've got a bulb, and we've got a speaker, and we've got a bulb, all in parallel with a battery. Now let's say it's a 6-volt battery. Now we've just talked about with the circuit analysis that because parallel circuits are independent loops, they're independent separate circuits which just happen to share the same voltage supply, but they have an independent connection to the voltage supply, then the voltage across each loop should be the same as the supply voltage, and that should be the case. So in theory, if we just have a battery, we just take it out the package maybe, and we don't connect anything to it, a 6-volt battery, then the voltage should be 6 volts. And then if we attach a bulb to it, the voltage across the bulb should be 6 volts if there's nothing else in the circuit. And then if we attach a speaker in parallel, if there's just the speaker in that particular loop, then the speaker should get 6 volts. And if we then attach a circuit with a bulb in, again, if the bulb is just the only thing in the circuit, then it should get 6 volts. However, in reality, if you attach nothing to the battery, then yes, you get 6 volts, but if you attach the bulb, you get 5.8, and then when you attach the speaker as well, you get 5.2, and then when you attach the bulb as well, you get 5.0. So in reality, you're not getting what circuit analysis says you should get. So what the hell is going on? Well, the idea is that the battery itself has a tiny bit of resistance. This is known as internal resistance in a circuit. And because of this internal resistance, the battery itself uses up some of the voltage push that it provides. Whenever you actually put a battery in the circuit, there are some lost volts. The more stuff you attach, so the more loops you have, or the more current you draw, however you're going to get more current, so the more current you draw, the more the lost volts are. I suppose, in a sense, a bit of a poor analogy, but it might help, is that lost volts are a bit like tax. If you do any kind of work, then you have to pay tax, and then the more work you do, the more you end up losing in tax.